We're going to start this lecture with a very simple demonstration. Now, we spent most of our last lecture thinking about acids and the protons that they create when they dissociate. We focused our attention on hydrochloric acid, hydrobromic acid, and hydroiodic acid, as well as sulfuric, nitric, and perchloric acids, which we collectively refer to as strong acids. But there are so many more acidic compounds to consider. Why did we so carefully avoid discussing them before? Now, in order to answer that question, we're going to have to head to the lab. We're back in Osmond Lab to try to answer that question that we just asked. Why is it that we confined our discussion to just 6 strong acids in our previous lecture? And to demonstrate why, I'm going to use 2 different acids, hydrochloric acid, which is one of the strong acids, and acetic acid, or the acid that's found in vinegar. Now, this is one that we haven't really discussed very much, but we're going to talk about it in depth now. But to show you a difference between these two that it's very relevant, I'm going to use a little bit of zinc. I have about 1 gram of zinc filings here in each of these 2 scintillation vials, we call them. And I'm going to react them with these acids. And in that reaction, there will be a proton, or actually 2 protons, I should say, reacting with zinc to create zinc ions and hydrogen gas. Now, we know from our kinetics lectures that if the concentration of protons is the same, then the rate of the reactions should be the same. So when I use 3 molar hydrochloric acid and 3 molar acetic acid, I would expect that if everything is the same otherwise, the reaction should run at the same rate. So let's run that reaction now and see what we observe. I'm going to pour some of my 3 molar hydrochloric acid into this dish here. It should be enough for us to see what we need to see. And I'm going to add some of my 3 molar acetic acid to the other dish. All right, there we go. Okay. Now I'm ready to run my reaction by adding the zinc. And we'll do these simultaneously so that we can observe the rate of hydrogen gas formation, which, remember, should be exactly the same if these 2 acids are behaving exactly the same way, right? 3 molar acid plus zinc, 3 molar acid plus zinc. Let's add and observe the difference. So now that the reactions are up and running here, you can see very clearly that the reaction with 3 molar hydrochloric acid is running far more vigorously, far more quickly, than the reaction of zinc with the 3 molar acetic acid. But this would appear to fly in the face of everything we know about chemical kinetics. 3 molar acid plus zinc and 3 molar acid plus zinc should have exactly the same reaction rate, shouldn't they? But there's something that we haven't yet accounted for. And that's the difference in how these acids ionize when they're in solution, because the rate is dependent on proton concentration. Now, to demonstrate that there's a real difference in proton concentration, even when the acid concentrations are identical, we're going to have to switch over to another technique. We're going to have to measure the pH of these solutions. To begin explaining why we saw different rates in our reactions, even though we use identical concentrations of 2 acids, we have to remember that the concentration of an acid and the concentration of the protons that result from that acid are not always the same. And to demonstrate that further, we're going to do a quick cursory measurement of the pH of these 2 solutions. Remember, 3 molar hydrochloric acid and 3 molar acetic acid. Now, I'm going to use for this purpose some test strips, which are essentially paper that have been doped with a very special pigment that changes color in response to various proton concentrations. And of course, if these 2 solutions do have exactly the same pH or proton concentration, we should see exactly the same color change in my 2 pH test strips. So let's start with hydrochloric acid. I'm going to take a clean glass stir rod and get 1 drop of this acid from the bottle. Never place the strip into the bottle because the pigments in the strip can actually come loose and dissolve into your large bottle of hydrochloric acid, ruining it. Oops, let me get that down in there. And now I'll place that drop on the test strip. Okay, so according to our pH scale on the test strip, our color comparison tells us that our 3 molar hydrochloric acid has a pH that's somewhere around 1 or 0. Now that's exactly what we would expect for a 3 molar strong acid solution. So that dries just a little bit more. I'm going to place that here so we can compare it later to the second strip. And the second strip I'm going to expose to a drop of our 3 molar acetic acid. Again, clean stir rod to get one drop out to be sure that I don't contaminate the large bottle of acid here. I'll put that one drop on my test strip. Okay, now we see something different, don't we? Let me compare that to my scale again. And you'll see that that 3 molar acetic acid has a pH somewhere between 3 and 4, significantly higher than the 3 molar hydrochloric acid. So what does this mean for us? Well, what it means is that we have to rethink the way acid concentrations affect pH when we start to consider acids other than those 6 strong acids that we discussed previously. To get that discussion going, we have to abandon our way of thinking about how acids ionize. Since we have only investigated strong acids, we could get away with assuming that they dissociate completely when dissolved in water. Every last molecule of HCl in the mix can be assumed to be H+ and Cl-, meaning that a 1 molar solution of HCl should produce a proton concentration of 1 molar in the resulting solution. But this behavior is the exception, not the rule. All other acids that we'll encounter in this course are defined as weak acids, which behave quite differently. Now, we know that hydrochloric acid is a strong acid, and we also know that it's going to dissociate completely, that's the definition of a strong acid, into H+ and Cl-. So, a solution of HCl doesn't really look anything at all like this, of course. It would look more like this, in which practically every single molecule of HCl in the solution has come apart and formed protons. So we've maximized the acidity of the solution here. But let's make an equal concentration solution of instead acetic acid, a weak acid that we know will ionize slightly to form H+ and its conjugate base, acetate, but not completely. In this solution, only a small fraction of the acetic acid becomes ionized at any point in time. But this is an equilibrium process for weak acids. So while this has just ionized, it's going to come back together while others are ionizing, which will come back together while even more ionize. So at no point in time do we have much more than a very, very small fraction of the acetic acid delivering real proton into solution. So the difference here we call strong and weak acids. Because acetic acid is a disfavored equilibrium, it's weak. Adding a lot of acetic acid will only add a few protons based on the equilibrium behavior. Whereas hydrochloric acid, on the other hand, is strong because it will ionize 100%, forming as strong of a solution of acid as possible. The fundamental difference in the behavior of weak acids and strong acids means that we can't treat them identically. Because weak acids release only some of their protons into solution, we have to model their behavior another way. So unlike strong acids, which release their acidic proton into solution never to be reunited, weak acids exercise a greater hold over their acidic hydrogens, giving them up only reluctantly and occasionally. Now, you had to know that this was coming the moment I used the word equilibrium. We can model the ionization equilibrium for any acidic molecule we can imagine, using an equilibrium constant. This will allow us to assign a value to just how weak any given acid is compared to others. So we have to describe the relative acidity of weak acids. How do we do that? How do we convey the intrinsic acidity of an acetic acid molecule? Is it more likely to release proton than some other acid like HCl, or is it less likely? Well, we do this using a number, an equilibrium constant actually, and we call it Ka. Now, Ka is no different than any other equilibrium constant, and we can determine it using a Rice table. The only reason we have that A subscript there instead of the regular EQ is because we're dealing with an acid here, the equilibrium between the unionized acid and the ionized acid, which delivers the H+ to solution. So, if I know exactly how much of my acid I added to solution, I know the initial concentration before any equilibrium is established. And again, I'm going to assume here that H plus is 0 and A minus is 0 for that instant in time when I first add my weak acid to solution. But a change will quickly happen. Some of that will ionize, and it will ionize in this proportion, 1 to 1 here. So I've got a change in concentration of minus some amount X for HA, and plus that same amount X for both proton and conjugate base. This leads me to an expression for equilibrium concentrations that's in terms of only X, right? Where I have the initial concentration of the acid minus X, I have 0 plus X for my acid or for my protons, and for my conjugate base. So this gives me a nice clean equilibrium problem with just one unknown. So Ka in this case is equal to, per the reaction, H plus times A minus divided by HA. Now, what does that mean in terms of what I've got here so far? Well, I can substitute my variables here, my unknowns, into the equation and get it in terms of a single unknown X. Right? So now it's X times X over HA minus X. And of course, we can simplify that even a little bit more by putting the proton concentration in where it belongs. And then even condensing this numerator here down because this is just H plus squared. So now I have an equation that will yield the Ka value, but the equation is only in terms of two things that I can easily measure: the initial concentration of that weak acid and the pH of the solution once equilibrium is established. That means I can determine the Ka for any acid just by making a solution of known concentration and then measuring its pH. It's actually quite simple. Let's go through that one time. Let's say that we make a solution that contains 60.0 grams of acetic acid dissolved in enough water to make a liter of solution. And we measure the pH of that solution at 2.38. What does that tell us about Ka for acetic acid? About how effectively it ionizes in solution? Well, again, we're going to have to use our Rice table to get the solution. So let's go ahead and set that up now and put in our reaction. Right? I'll just use a generic reaction here first, but this is acetic acid, so remember this is CH3COOH ionizing into H plus and acetate. Now our initial concentration of acid, which is one of the critical factors that we need, can be determined from the 60 grams in 1 liter of solution. Now to convert that into molar, I simply use the molar mass of acetic acid, which I've estimated at 60.0 grams per mole. In this case, grams cancel, and I get moles per liter in my answer, exactly what I'm looking for. So I'm ready to do my math. This gives me a 1 molar solution, nice and clean. So let's put that in as our initial concentration of HA. And acknowledge that before equilibrium is established, the instant that acid hits the solution, there is no H plus and A minus to speak of. Our changes are always going to be the same here because this is a single acid releasing 1 proton. And we can figure out that proton concentration from down here, right? Notice that I've got a proton concentration as a variable X, but my problem here tells me I know the pH is 2.38. And the pH is directly related to the proton concentration. The proton concentration is 10 to the minus 2.38, which is 0.00417 molar. So let's put that into our table and acknowledge as well that if this value is 0.00417, this must be as well. And this value over here must also be 0.00417. Well, that simplifies things dramatically. It gets rid of my unknown and makes this just a simple math problem now. All I have to do is take the equilibrium constant, just right, for the acid dissociation, Ka, what I know to be the numbers at equilibrium from what I've measured in my problem, and calculate the value. 1.75 times 10 to the minus 5. This value gives me a way to gauge exactly how much acetic acid likes to release protons in comparison to other weak acids, and lets me know exactly how a solution should behave when I make one using acetic acid. Now that was a really tiny number, 1.7 times 10 to the minus 5. So what this number is telling us is that only a very small fraction of the acetic acid molecules in our solution are ionized at any given time. We calculated that a 1 molar solution of acetic acid has a hydrogen ion concentration of 0.00417 molar. That means less than 0.5% of all the acetic acid molecules in our solution are ionized at any point in time. But Ka goes beyond just giving us a way to calculate the pH of solutions of weak acids. It also gives us a very useful tool for comparing the relative strengths of weak acids themselves. Here are a few everyday acids that should look pretty familiar. Acetic acid, with its Ka of 1.75 times 10 to the minus 5, clearly weak. Phenol, a common ingredient in lip balm formulations, has a Ka of 1.3 times 10 to the minus 10, making it about 100,000 times less acidic than vinegar. Beverage alcohol, or ethanol, comes in at about 10 to the minus 16, 1 million times less acidic than phenol. But just like proton concentrations in Sorensen's laboratory, acid Ka values range all over the place. They cover a huge range of numbers. Our short table of Ka values here covers a range of 11 orders of magnitude. So, just like Sorensen's pH scale, we often report the strength of acid using not its Ka, but its pKa, or the negative log of the acid dissociation constant. When we modify our Ka values in this way, we get much more manageable numbers. And just like the pH scale, lower numbers means a stronger acid. Acetic acid comes in at 4.76 on the pKa scale, phenol at 9.89, and ethanol at about 16. Now, the difference here is that the pKa values reference the intrinsic acidity of a particular molecule, giving us information about how easily a particular compound ionizes, while pH, of course, refers to the total proton concentration of a solution of these molecules. It's possible to have a very acidic solution of acetic acid, for example, which means a low, very acidic pH value, but the pKa of acetic acid lets us know that we'll have to be very, very concentrated if we want to do that with such a solution. So we just saw how chemists can determine and quantify the intrinsic acidity of a given substance using Ka and pKa values. But to what end? What makes these values worth discovering? And the answer is quite simple. Once we've determined the dissociation constant for a given acid, it can be used to predict the pH of any solution of that compound that we can imagine. To do this, we simply reverse the equation we explored previously, making the proton concentration the variable and using the predetermined Ka value to solve. So let's use our most familiar one here. We're going to do this with acetic acid again. The question at hand is this. What is the pH of a solution made by dissolving 15 grams of acetic acid in enough water to make 1 liter of solution? So we're going to use a rice table just as before to manage this problem. Let's get that all set up and ready to go. Remember, this is an acid dissociation reaction in which HA, in this case acetic acid, dissociates into protons and its conjugate base, in this case acetate ions. Let's get started by calculating the initial HA concentration. That's going to be 15 grams of acetic acid dissolved in enough water to make 1 liter of solution, so 15 grams per liter, and with a molar mass of 60 grams per mole. We can do our unit analysis, determine our equation is set up correctly to determine the molarity of acetic acid. We get 0.250 molar acetic acid as our starting concentration. So let's put that up here in our initial block for the acid. Now remember, we're assuming that nothing happens at the first instant that we mix the solution. So H plus and A minus can be estimated at 0. Our changes are dictated by the reaction stoichiometry, in this case a very convenient 1-to-1-to-1 stoichiometry. We lose X moles of HA, we gain X moles of protons and X moles of acetate ions. That makes our equilibrium concentrations these values, 0.25 minus X for the acid and X for the proton and the conjugate base concentrations. So Ka we know for a fact for acetic acid to be this. This is our expression that we're going to use to get our solution. But we also know from our rice table that this expression is equal to Ka for acetic acid, X squared over 0.25 minus X. So that is also equal to Ka. But I've eliminated that X down there to try to save myself the trouble of having to solve a quadratic equation. If you want to be absolutely rigorous about this problem, you would actually solve this using that quadratic equation. But I've got a shortcut and I can justify it, and I'll show you how. Remember, I dropped the x, or rather the minus x, off of the denominator here. That means I'm assuming it's much, much smaller than 0.25 and therefore won't really affect the outcome. So let's set my simplified expression equal to 1.75 times 10 to the minus 5, our value of Ka that we determined previously for acetic acid. When we solve this for x, we find that x equals 0.00209 molar. Now I can go back and justify that earlier assumption. This number is much, much smaller than the original number that I would be subtracting it from. Because my answer is just about 1% of the number it was being subtracted from, I can assume that it has a negligible effect on the outcome of my calculation. The outcome of that calculation is that the proton concentration, X, is equal to 0.0029 or 209 molar. And taking the negative log of that number gives me the pH of my final solution. 2.68 is the pH that I expect to get when I dissolve 15 grams of acetic acid in enough water to make 1 liter of solution. So we can use the Ka value as a tool to predict exactly what pH will be achieved by a given concentration of a weak acid. This is because it accounts for the partial ionization of weak acids. Think for a moment about the conjugate base of a strong acid, one like hydrochloric acid. Now, we know that the very definition of a strong acid predicts that its conjugate base, in this case, chloride ion, has absolutely, positively no affinity for protons whatsoever. From a Bronsted-Lowry perspective, chloride is neither an acid nor a base. It is completely neutral. If chloride had any basic properties at all, at least a small fraction of that chloride would pick up a proton here and there, reversing the process. And this would actually be the very definition of a weak Bronsted-Lowry base. Now, if you think about it, this means that the weaker an acid becomes, the stronger its conjugate base must be. So, strong acids have completely neutral conjugate bases, but weak acids do not. As the acid we're talking about becomes weaker, its conjugate base becomes progressively stronger. So if acetic acid is a stronger acid than phenol, which is stronger than ethanol, then acetate must be a weaker base than phenolate ion, which is itself a weaker base than ethanolate ion. So we just had the realization that progressively weaker acids will have progressively stronger conjugate bases. But you had to know by now that I wasn't going to let you get away without putting a number on that strength. So just how can we convey the intrinsic strength of a Bronsted-Lowry base numerically? To mathematically model the behavior of bases, we use the base association constant, which it turns out is very closely related to Ka and Kw. Let me show you how. Consider a standard acid dissociation reaction where Ha dissociates to become H+ and A-. Now consider a standard base association reaction using that same conjugate base, right? If A- is a base, that means it can also react with a molecule of water to create HA and hydroxide ions. Now, if I use conjugate acids and bases to make these two equations, and then I add them together, let's see what I get. I get something very familiar. Folks, that's the ionization of water, and we know the equilibrium constant for that process. So, if we know Ka, and we also know that Kw is a constant, we have a mathematical route to get to Kb. Specifically, Ka times Kb equals Kw. So using this expression, I can get a mathematical relationship that allows me to calculate the base association constant of any base for whose conjugate acid I know the acid dissociation constant. Now that I have a way to determine Kb, so long as I know Ka of the conjugate acid, and of course I always know Kw because that's a constant for the autoionization of water, all I need is a way to get an expression for Kb, and I'm in business. I can start calculating concentrations. So let's look at the reaction specifically that's governed by Kb. In this reaction I have my base, which of course will be included, water, which we treat as a pure liquid, so that will not go into the expression, Ha, its conjugate acid, and OH- hydroxide ions. So let's place all of those species into an expression for Kb. And when we do that, we get this expression down here, Hydroxide times conjugate acid divided by conjugate base, all at equilibrium. But just as we did with acids, we can make some substitutions that allow us to use this equilibrium constant expression more effectively. Now, without going through an entire rice table, let's just make the same kinds of substitutions that we did with weak acids and see what happens. Here's a duplicate of my expression. Let's insert the following assumptions: that hydroxide and conjugate acid concentrations are equal based on reaction stoichiometry. That allows me to make this substitution. And of course, that every time we lose a mole of our base, we gain a mole of hydroxide ion. That allows us to make this equality and substitute it as well into our expression. So that gives me my hydroxide squared, which I can put together here to simplify a bit. And our final assumption, that the hydroxide ion concentration as a result of a weak base is far less than the actual concentration of that weak base. That allows us to eliminate this particular term from the equation. And when we do this, and then a very simple rearrangement, what we find is we can calculate the hydroxide ion concentration at equilibrium if we know Kb for the base and the concentration of that base that we used. So we have a very simple expression here that allows us to get to OH minus concentration. And from there, of course, it's a relatively simple calculation to determine proton concentrations, pHs and pOHs, based upon this number right here that we were able to access using Kb. This relationship between Ka, Kb, and Kw leads us to an overall picture of how a solution of any weak acid or weak base will behave. So let's summarize this lesson. We started by comparing similar solutions of a strong acid, which we discussed last time, with a weak acid. Now, in doing so, we saw that similar strength solutions of weaker acids are less acidic than their strong acid counterparts. And we explain this observation by invoking partial ionization of weak acids, recognizing that for most acids, only a very small fraction of the solute molecules are dissociated at any given time. This prompted us to bring our knowledge of equilibrium to bear on the problem. We devised an equilibrium constant for the ionization of weak acids called Ka. Then we related the term pKa, which makes intrinsic acidity of different compounds easier to compare. Next, we saw how useful Ka values can be in predicting the pH of solutions of weak acids. We then considered water and its amphiprotic properties, that is, how it can act as both an acid and a base. And we reminded ourselves how water autoionizes in an equilibrium governed by yet another constant, Kw. We then turned our attention to bases and saw how they can accept a proton from water to form hydroxide ions in a third equilibrium, governed by the constant Kb. And finally, we put all three of these reactions together and saw how Ka, Kb, and Kw are all related to one another and can paint a complete picture of exactly what's going on in solutions of any weak acid or base. So today we covered how to determine the properties and concentrations of various species in solutions of acids and bases in isolation. Next time, we're going to take our understanding of acid and base solutions to the next level and begin to consider what happens when both of them react with one another.